Hey everyone, and welcome. Have you ever stopped to think about how your phone knows the absolute fastest way to get you somewhere? It's not magic, it's logic. And today, we're going to pull back the curtain on two powerhouse algorithms that literally shape our digital world. Let's dive in.
Really think about it for a second. You pull up a map app, and what you're looking at is this huge, sprawling puzzle of streets and highways. And boom, in a split second, your phone hands you the perfect route. How? That's what we're talking about today. It's the incredible power of shortest path algorithms at work.
All right, so here's our game plan. We'll kick things off by defining what the shortest path problem even is. Then we'll look at two main solutions, a simple one called BFS, and then the big one, Dijkstra's algorithm. We'll see how Dijkstra actually thinks, figure out when to use each tool, and wrap up by spotting these algorithms out in the wild.
Okay, first things first. What are we actually trying to solve here? The shortest path problem sounds pretty straightforward, right? But getting this definition down is totally key to, well, everything else we're going to talk about.
So at its heart, the problem is just finding the cheapest way to get from one point, or node, to another. But here's the cool part, that word cost. It's super flexible. It doesn't have to be distance. Cost could be time, it could be money for a flight ticket, it could even be how long it takes a data packet to travel across a network. And that flexibility, that's what makes these algorithms so incredibly useful.
Now, before we can solve anything, we have to know what kind of map we're dealing with. And there are really two main types. On one hand, you have unweighted graphs. Here, every single step costs the same. A great way to picture this is a chessboard. Moving one square is always just one move. But then you have weighted graphs, which are way more like real life. A highway is obviously faster than a side street, right? The paths have different costs, or weights, and understanding this difference is, well, it's everything.
Okay, so let's tackle that first case, the simple one. When every path is created equal, we can use this really elegant and super efficient tool called breadth first search. You'll usually just hear it called BFS.
And this is the perfect way to think about it. Seriously, picture dropping a stone into a calm pond. You see those ripples? They spread out, level by level. BFS does the exact same thing. It explores all the locations one step away, then all the locations two steps away, and so on. It's super methodical, and because of that, it's guaranteed to find the shortest route.
So here's how it works in practice. 1. You start at your beginning point. 2. You look at every single place you can get to in one step. Those are your direct neighbors. 3. You look at their neighbors that you haven't seen yet. You just keep doing that, expanding outwards level by level. And the magic is, the very first time you hit your destination, that's it. You've found a shortest path. Simple, clean, and it just works.
Okay, that's great for simple maps. But life isn't usually that simple, is it? What happens when you've got highways and slow city streets? Well, that's where BFS kind of falls apart. For these weighted graphs, we need something a little more clever.
Right? Think about it. A route that's only 2 turns away might take an hour in traffic. But another route with, say, 5 turns might be all highway and take just 20 minutes. Suddenly, the number of steps is irrelevant. It's the cost of each step that matters now.
And this is where we bring in the heavy hitter, Dijkstra's algorithm. This thing is purpose-built for weighted graphs. But there is one golden rule you have to follow. All the costs, or weights, have to be positive. It makes sense, right? You can't have a road that takes negative 10 minutes to drive on.
So how in the world does Dijkstra's work its magic? It can seem a bit complicated at first, but the logic behind it is actually super smart and systematic. So let's pull it apart and see what makes it tick.
Okay, here's the core idea. It starts at the beginning like BFS, but, and this is the key difference, it doesn't just explore randomly. It always picks the unvisited place that's currently the closest to the start. Then, from that new spot, it checks on its neighbors and basically asks, hey, is it faster to get to you by coming through me? That check and update step is called relaxation. Then it just repeats that whole process, find the next closest unvisited spot, and relax its neighbors.
Let's really zoom in on that relaxation idea, because it's super important. Imagine the algorithm thinks the best way to city B takes 50 minutes. Okay, it holds that thought. Then it explores city A and finds it only takes 30 minutes to get there. And the drive from A to B is just 10 minutes. The algorithm goes, wait a minute, is 30 plus 10 better than 50? Heck yeah, it is. So it relaxes its old belief and updates the best path to be 40 minutes. It's just this constant process of finding better and better routes.
Okay, so you might be thinking,
How does it find the next closest node so fast every single time? If it had to check every single unvisited node in the whole map, that would take forever. Well, you're right, and that's why Dijkstra's has a secret weapon, and it's called a priority queue.
The easiest way to get this is to think about a checkout line. A normal queue is first in, first out. Simple. But a priority queue, that's like a VIP line at a club. It doesn't matter when you got there, the person with the best ticket, which for us is the node with the smallest travel time, gets to go to the front of the line. This is what lets the algorithm instantly grab the next most promising node to check out.
All right, so we've got these two amazing tools, BFS and Dijkstra's. Now for the million-dollar question. When do you use which? Let's make this practical.
Think of this as your quick and dirty cheat sheet. The rule is simple. Are all your steps equal? Use BFS. It's ridiculously fast for that scenario. Do your steps have different costs, like a real roadmap? Then you need Dijkstra's. And don't get spooked by that time complexity column. That's just a fancy way of saying how fast they are. The bottom line is, BFS is lightning quick for simple cases, and Dijkstra's is still super efficient for the complex stuff, all thanks to that priority queue we talked about.
And hey, let me save you some future headaches. Here are some common traps people fall into. First, don't use BFS on a weighted graph. It'll just find the route with the fewest turns, not the fastest one. Also, never, and I mean never, use Dijkstra's if you have negative costs. It just completely breaks the way the algorithm thinks.
Yeah, I'm going to say that one more time because it's the #1 rule. Dijkstra's whole strategy is based on this idea that once it finds the shortest path to a place, it's final. That only works if all the costs are positive. A negative cost would be like discovering a road that lets you travel back in time, and it just messes up the whole calculation.
So what do you do if you have negative weights? And believe it or not, that can happen in things like financial modeling. Well, for that, you'd need a totally different tool, something like the Bellman-Ford algorithm. But that's a whole other can of worms for another day.
Okay, we've been throwing around a lot of abstract terms like nodes and edges and weights, so let's bring this all back down to earth. Why should you care about any of this?
Because this stuff is everywhere. It's the silent engine running your Google Maps and your GPS. It's what zips your emails and cat videos across the internet in the blink of an eye. It's even the reason characters in video games don't just run into walls all the time. Pathfinding is literally the hidden logic of our connected world.
So the next time you fire up a map to find the nearest coffee shop, just take a second to appreciate the beautiful logic of BFS or Dijkstra's humming away in the background. It's one of those amazing, invisible systems that just makes modern life work. And it really makes you stop and wonder, what other secret algorithms are out there, quietly shaping our world?